Hello, I am Sayan Ghosh, and I'm from Saha Institute of Nuclear Physics, HBNI, West Bengal, India. And my topic is simulation of nuclear recoils due to supernova neutrino-induced neutrons in liquid xenon detectors. First, I'll introduce our topic and then briefly discuss on the supernova neutrinos and the resulting coherent elastic neutrino nuclear scattering recoil spectrum. And then I'll discuss the neutrino-induced neutrons, the new IN in respect to the liquid xenon. And then I'll describe the GN4 simulation firstly with monoenergetic neutrons in liquid xenon detectors, and then the simulation with the new IN spectrum in liquid xenon. And then finally, I'll describe the generation and analysis of the S1 and S2 signal and conclude, and I'll present some outlook. Now, core collapse of supernova produce huge flux of neutrinos of all flavors of energies up to few tens of MeV over a time scale of about 10 seconds. Now, these neutrinos can be detected by various experimental facilities via their charge current and neutral current interactions with the detector material. In large volume liquid xenon based dark matter detectors, these neutrinos can give rise to detectable signals due to neutrino-induced nuclear recoils via the coherent neutrino-induced nuclear scattering. This we symbolize as CENS. Now, in addition to the CENS, the neutrinos can also produce neutrons inside the liquid xenon tank through inelastic charge current interactions. These neutrons can again generate additional nuclear recoils, giving an additional channel for supernova detection. Now, it is found in our work that neutrino-induced neutrons can give the dominant contribution to the nuclear recoil spectrum for energies above 30 keV of recoil energies above 30 keV, and this is over the contribution from the CNS alone. Now, in our work, we have considered the supernova due to the collapse of an 18 solar mass progenitor star at 1 kiloparsec distance from the Earth, and we have considered 1 ton of liquid xenon. And the temporal profiles are of the average energy and luminosity of different neutrino species are taken from this paper. The plot has been taken from this reference, and the resulting CNS recoil spectrum is shown in the blue. We can see that at lower end of the spectrum, the count rate is quite high, but this count rate falls off very rapidly with increasing recoil energy. Now, as I said before, inelastic charge current interactions of the supernova neutrinos with the 132 xenon can produce the 132 cesium. Now, this 132 cesium will be generated in an excited state, and this 132 cesium, excited 132 cesium, will decay to its natural state through the emission of neutrons. And these neutrino-induced neutrons can undergo elastic and inelastic scattering on the xenon nuclei and produce recoiling xenon nucleus. And here is the schematic of it. The yellow lines are the incoming neutrinos. The blue balls are the stationary xenon nuclei, which get this kind of recoil, which is presented by the red arrows, and the resulting neutrons from the emission is presented by these black balls. Now, these neutrons, as we can see here, can give rise to further recoils, and therefore the scenario of a single recoil or multiple recoil comes into play. And the total reaction has been represented here, where X is basically the number of neutrons that are being finally emitted from the decay of the excited cesium. Now, this is the spectrum of the neutrons that we neutrino-induced neutrons in the xenon tank that we get for our consideration of 18 solar mass progenitor supernova at 1 kiloparsec distance from the Earth. And this is only when and this is the result for the consideration of normal ordering of the neutrino mass hierarchy. And if we take a 1 ton xenon tank, we get around 8 neutrons. Now I will discuss this GN4 simulation. We take a 1 ton liquid xenon tank with a 1:1 height to diameter aspect ratio with the diameter being around 75.4 centimeters, and the detector material we took as the liquid 132 liquid xenon isotope with a density of around 2.953 gram per centimeter cube. Here I would like to mention that we also did the simulation with the natural isotopic abundance of the liquid xenon, which is available as a material in the NIST database, but we did not find any appreciable difference in the two. So I would present the results with the 132 xenon isotope only. Now we start with first the monoenergetic neutrons. Now for the monoenergetic neutrons, they were generated homogeneously inside the liquid xenon tank and propagated isotropically. Now these neutrons can generate nuclear recoils by elastically scattering of the stationary xenon nuclei, and also the inelastic processes can also take place, which is basically this xenon nucleus absorbs the neutron and resulting in an excited state nucleus, which will again decay by the emission of neutrons and gamma rays. Now these new neutrons can further undergo elastic and or inelastic processes and give rise to multiple recoils. This is the resulting recoil spectra for the different monoenergetic neutrons, and we can see that with the low energy of the initial neutron, the recoil spectrum is predominantly flat, but the spectrum becomes skewed towards the lower energy side as we increase the energy of the initial neutron. Now this is expected because at lower energies of the initial neutron, all scattering angles are equally probable, and therefore the recoil spectrum is flat. But for higher energy of the initial neutron, forward scatterings are more favored, and therefore we get low energy recoils. Now we also investigated the probability of getting 1, 2, 3, etc. Recoils from one single neutron, and we found that the possibility of having only one recoil from one neutron is much more probable than having multiple recoils, and this is due to the fact of the finite dimension of the detector, and therefore the neutrons that will be produced near the walls of the detector will at most create one xenon recoil. And we also find that the rate of decrease for these multiple scatters becomes much faster if we go to higher energy of the initial neutron. Then we simulate for the actual neutron spectrum from the neutrino-induced neutron spectrum, and we here we present the recoil spectrum for 1, 3, 5, 9 and 11 scatterings. There will be higher number of scatterings as well from a single neutron, but we have represented here up to 11. What we want to depict from this plot is that the lower energy side of the spectrum gets more contribution from the multiple recoils, but this increase in this contribution is not monotonic with the order of the recoil, because of the steep fall of the probability as we go to higher scatterings. Accounting for all of these, we get the final recoil differential rate spectrum. The CNS result I have already displayed before. There in the red line has been drawn for the nu IN contribution, and we can see that at recoil energies greater than 30 keV, the nu IN contribution is much larger. Now for a typical liquid xenon TPC based dark matter detector, the S1 and S2 signals are the final observables. Now the S1 arises from the scintillation and S2 arises from the ionization. Now the S1 and S2 signals in this work have been computed with the Monte Carlo simulations based on the mathematical models described in these two references, where they have modeled the S1 and S2 by Gaussians, where the quantities NPE represent the final number of detected photoelectrons at the photomultipliers, and the NEL tilde represent the ionization electrons reaching the liquid gas interface. Now these quantities are dependent on the recoil energy and also depend on various other quantities and properties of the liquid xenon detector. Some more points need to be kept in mind while computing the S1 and S2 signal. For the S2, the width of the S2 signal is typically around 1.5 to 2 microseconds. And for multiple recoil from the same neutrons, drift time of the electrons is a determining factor. Therefore, the S2 signals, due to two consecutive electrons arriving at the gas phase boundary with the time difference of more than 2 microseconds apart, can be treated as separate S2 signals. But electrons arriving within this 2 microsecond time window of each other will be merged into one. Therefore, considering or taking into account the drift time of the electrons inside, drift velocity of the electrons inside the liquid xenon, typical liquid xenon detectors, this corresponds to the fact that the multiple recoils separated by more than 3 mm in z direction can only be separated. Now for the S1 signal, these are generated from the scintillation photons, and the fact that light travel time across the entire detector height is less than the S1 pulse width, this basically makes it impossible for separate S1s to be detected from separate multiple recoils to be detected separately. All the S1s generated from the multiple nuclear recoils will be summed up into one. Now for the CNS events, these are basically the direct recoils produced from the neutrino interaction with the xenon nucleus. Now this can be at most 1 for each neutrino, and therefore for each CNS event we will get only one S1 and one S2. Taking all that into account, we get the final differential spectra for the S1 and S2, and we can see that for both of these, the lower end of the spectrum is dominated by the CNS interactions, but the higher end of the spectrum is mostly due to the nu ion interactions. Now we integrate the differential spectrum with respect to the detector threshold, and we find that again at higher thresholds of the detector, the dominant contribution comes from only the nu ion interaction, but and the thresholds are around 30 photoelectrons for S1 and 1900 photoelectrons for S2, and the total integral spectrum gets a tail-like extension due to the nu ion contribution. Therefore, to conclude, we can say that the neutrino-induced neutrons present an extra handle for supernova neutrino detection in addition to the CNS process, and at higher thresholds the nu ion contribution is much more dominant, and therefore the total feature gets a tail-like extension to the total S1 and S2 signal integral spectrum. And future multi-scale, multi-ton scale liquid xenon TPC based dark matter detectors like the LZ, which is 7 ton, and Darwin, which is supposed to be a 40 ton experiment, may offer very good opportunities to look for these supernova neutrino-induced neutron signals, since the total number of neutrons produced in the liquid xenon tank will be much more. And I also would like to point out that the CNS contribution comes from all flavors of neutrinos, whereas the nu ion events get dominant contribution from only the electron type neutrinos, and therefore identification of the nu ion events can give an observational handle on the flavor composition of the total supernova neutrino flux. I would like to thank Will Taylor of Brown University for very useful correspondences, and thank you. That is all from my end.